Welcome to the Vaxa Bureau Intelligence Optimised podcast, where we talk with people building the future across critical industries, sovereign capability, and the Indo-Pacific. Today's episode is all about energy, not just how we generate it, but how we move it. My guest is Billy Jeremijenko, founder of Aquila Earth, an Australian startup doing what sounds like science fiction, transmitting energy through the air using lasers. Right now, their tech lets drones fly indefinitely without landing. But the bigger play? A global energy network that can beam power from orbit wirelessly to where it's needed most. We talk about what that means for logistics, defence, disaster response, and energy sovereignty. This is the kind of edge thinking that turns national ambition into real capability. Let's get into it. Billy from Aquila Earth, welcome. How are you, mate?
Yeah, I'm pretty well. It's a nice day here in Sydney, and just at work doing my thing.
Yeah, and Billy, and so mate, you've been traveling a bit as well recently, Singapore and the US.
Singapore, US, spent a bit of time in Japan. Kind of all over the place, to be honest.
Wow, mate, the price of global domination, travel.
Yeah. When you got something that no one else has, it's not just a play for Australia. It's really a play for the world,
Mate. And yeah, I've had the benefit of some insights into what you and the Aquila Earth team are up to. Billy, tell us, what's the big idea behind Aquila Earth, and why do you think the world needs what you're building, and why now?
Yeah, absolutely. So for context, we think that there's a real bottleneck in power transmission itself, and we think that scaling power transmission is critical. So not just in terms of like how many poles and wires we have, but in terms of like how we can access electricity as a civilization. There's a lot of megatrends in electrification, autonomy, all this transformation that's occurring around renewables. And yet there's still about 1 billion people with no connection to a grid. 90% of renewable projects are blocked, and there's about $15 trillion of global transmission demand. So this is a big space in which to play in for, the electrification and renewable transformation that's happening right now. And the big idea behind Aquila is we realized a couple things. One, if you look at the transmission sector, poles and wires are not getting faster and cheaper to build. In fact, they're getting slower and more expensive to build. And that's kind of paired with a need to dramatically accelerate the deployment of transmission infrastructure. And we compare that against a new energy form factor, which is optical power. And this is very different. It's like it's nascent, but optical power has reached economic escape velocity. Instead of getting more expensive to deploy and scale, costs drop about 40% per doubling in power deployed. Power densities going up more than 10 times per decade. And we've finally seen new free space standards enter the market, which enable free space operations and free space like optical power networks. So our big idea is that we can create a new energy form factor, and we can shift energy around the world by creating an energy network of light to empower a lot of the trends we're seeing in electrification and sort of renewable transformation.
That's huge, mate. You mentioned two things that really piqued my interest then is, and correct me if I'm wrong, did you say 1 billion people in the world are without access to energy?
Without access to a grid. So this is interesting. Some of these people do have gas or let's say microgrids. Like maybe you see a lot of people in rural kind of Africa who have like micro solar sort of installations. But they don't actually have a connection to a grid. So like for the purposes of energy security, they just don't have it. That's really fascinating to me. And like I think of this in terms of the Internet of Energy. Because if you look at communications, you see this trend towards like higher and higher levels of interconnection between people all over the world. And in electrification and sort of grid infrastructure, we actually see the opposite trend of like gradually communities are becoming disconnected from the grid. And it's just too expensive to build and maintain all this infrastructure. So it's like actually trending towards isolationism, which is really fascinating and really misaligned with the general trend of history. Whether you look at like communications or trade or like all of these different sectors, you tend to see more globalization over time, but you see the opposite in energy transmission. So I guess our maybe contrarian thesis about the future is that actually we need to do the opposite. We need to move towards a more interconnected energy system instead of a less interconnected energy system, because the only way we'll be able to make the world, electrified and renewable is by getting energy from wherever it is to wherever it's needed.
And is that, as you mentioned a second ago, you're building the Internet of Energy. What does that mean in practice?
Yeah, yeah. So if you think about our long-term vision, it's essentially, okay, let's say you've got a solar farm in Outback Australia, and it's several thousand kilometers from a municipality. So like grid infrastructure is too expensive to build, but there's a lot of solar energy there. And what we can do is we can say, look, with this technology deployed at scale, we'll be able to attach an optical transmitter to that solar farm, beam its power into space, direct it around the world with essentially a network of space-based mirrors, and I get the energy from, like, say, Outback Australia to power peak hour New York City or factories in Europe and sort of enable that shifting of renewable power around the planet. That's really the long-term vision at Aquila, and you know, we're working towards that. We've got several like valuable beachheads that allow us to validate and sort of retire the operational risk of getting this technology into the market. Then scaling it eventually takes us towards that long-term vision.
Wow. I mean, you look at fixed, like you said, poles and wires and even undersea cables. I mean, they're extremely expensive and not only to build but to maintain. But you look at Mike Cannon-Brookes, he's currently building the sun cable from Darwin to Singapore. How much do you reckon that would cost?
Yeah, I mean, so the minimum on grid infrastructure, like for long range transmission, is generally about 1 million a kilometer. There's let's see, so there's several million kilometers of grid infrastructure in countries such as U.S. and China. I think China has let's see, grid infrastructure kilometers. Yeah, China has something like 1.8 million kilometers of transmission lines and 3.5 million kilometers of distribution lines. So if you multiply like those figures, and so the US is a similar amount. Australia is like relatively similar as well because we've got like a massive amount of land. But you multiply those figures by like 1 million per kilometer, and there's a lot of expense, like trillions and trillions of dollars that goes into the grid infrastructure that exists today. So it's like for the high voltage transmission lines, like undersea cables, no one's really been able to validate that for between country energy trading. There's a fair few geopolitical and sort of just geological like issues in terms of cross border trade that happen if you're actually deploying this infrastructure like through sovereign land, which is another thing that makes ground based transmission so difficult. But for the specific HVDC that like Mike Cannon Brooks is looking to deploy, that would be, probably in the range of 10 million a kilometer, if I were to give an estimate.
Geez, that's expensive. And that's just from one point to one point. So what you're suggesting Aquila can do is you beam the energy into space, it essentially hits a mirror. You can redirect that mirror or that satellite to anywhere in the world. So it's not just one fixed location. So if, say for example, Singapore say, Australia, we don't want your energy anymore, that power cable's useless.
Yeah, yeah, something like that. I mean, it's a real like if you compare it to the internet again, internet is like a decentralized network that enables you know distribution of information from wherever in the world it is to wherever in the world it's requested. And we want to make energy feel very similar with this kind of Internet of Energy infrastructure. And as you said, instead of having fixed point A point B transmission, you might have essentially a mesh network that enables like matching from like wherever the supply is to wherever the demand is. And the advantages of that network relative to like fixed transmission is now it's like point to multi-point. So like you can distribute energy around the planet, and also it's zero cost per kilometer. So once you deploy the initial like transmitters, receivers, the relays, you don't have to expend any cost per kilometer for like a beam of light. It's very different to like grid infrastructure from that perspective. And the final thing is at scale, we estimate sub 10 cents per watt, close to a cent per watt would be possible in terms of capex. So it's really economical from the perspective of just like having the generators attach a transmitter as part of their project. So it's really quick, and then all of a sudden they have access to all the world's markets. Essentially, that's the vision that we're working towards.
Wow, Billy, that's amazing. You're currently proving this technology by powering drones wirelessly. Now that's already a massive undertaking. But so,
Yeah.
what did it take to make that work, and what's it unlocked for you?
Yeah, yeah. I mean, I guess to draw the connection here, what we're building is essentially an energy platform, and our energy platform solves pressing problems in beachhead markets, and drones is one of those beachhead markets. I mean, we're seeing this current mega trend in sort of national security towards drones, and what we provide is kind of an infrastructure layer for those operations right now. And because it's a pressing problem, we can get our solutions into the market quickly. We can retire the technical risk. We can prove that we can operate these systems in the market from like an operational and also regulatory perspective, and that really unlocks the future vision of scale. So that's really the connection there. But in terms of like how we're deploying these solutions, it's really difficult technology. I'm not gonna lie. It's you're talking about beaming a kilowatt or more of optical power density through like a 20 millimeter aperture. So you need to dissipate essentially like several hundred watts of heat load through a very similar size surface, which is difficult, to say the least. And you need to operate at high efficiencies, high intensities. You need to collimate over distance. You need to track within like millimeter precision to make sure you deliver a consistent amount of power to the drone so it can fly forever. You need to do that over several hundred meters range, and extend that over time, because customers want more and more power. They want more and more range. You just got to keep iterating towards like high levels of capability that really unlock more value for customers. So there's a lot of technical problems and operational problems you need to solve just for the drone application, but it does really open up the space in a way that I think wouldn't be possible if we tried to go for the big market first.
Yeah, man, it sounds like something out of the Jetsons. I love it. Maybe you could tell me, like, how does the leap from powering a drone to powering infrastructure across borders and into space actually work?
Yeah, really good question. So I think of this in terms of speed, power, and distance. A drone is relatively low speed, power, and distance to power the drone and enable it to fly forever, which is relatively high value. And then scaling towards higher, faster drones in the aerospace sector, which themselves can act as relays. Like once they can fly forever, they can serve as like pseudo satellites. So you can relay energy through the aerospace stratosphere environment, and sort of that enables efficient transmission over 1,000 to 2,000 kilometers. So even in like using the drones as like relay systems that can direct energy around, like even through those like sets of applications, there's already something like a $28 billion remote power market that you can serve, relative to say like shipping diesel around or whatever. And once you can do higher speed, power, and distance, then you can gradually build up the capability to beam through satellites, which are higher speed, power, and distance still. It's just really about developing the capability, validating the operation, scaling power transfer. And in terms of scaling power transfer, like again, it's we think of this similar to like say data centers or solar farms. Like the advantage of our system is that it's inherently modular. So once you can achieve a level of power transfer, then scaling is just a matter of putting transmitters and receivers together. I mean, it's more complicated than that, but at a high level, that's the strategy you take. So we see it as like really well connected to the long-term vision. And once we can validate operations by serving drone applications, we can start scaling towards that long-term vision.
Right, right. So, Billy, what's the roadmap from near Earth to deep space and back look like?
Yeah, the roadmap is going from drones to higher fast electric aircraft to satellites, and then eventually to across the world. So specifically at around 300 watts and 300 meter power and distance scale, we unlock the base security market, which is around $150 million in market opportunity. There's several thousand military bases worldwide, and they all need security. And with an eye in the sky that can fly forever, we can provide that security. And then we move on to border, which is border security, which would be higher, faster electric drones. So looking at the fixed wing variants that would have higher level sensors on board. And there's around 36,000 kilometers of allied border space that needs to be secured. So there's a relatively good opportunity there as well. And then eventually like electrifying aerospace more generally. So if you look at, for example, direct freight within the aviation sector, we typically see a lot of routes which are not economical to run with 747s or so, because you have to fuel up the 747. It's not operating at max efficiency if it's only doing small amounts of haulage over small distances, and the cost per sort of hour of operation is relatively constant as well. So like there's a lot of direct freight that is not economical because there's just not the I guess the types of platforms that can serve those use cases. So being able to power smaller drones at they're around the 100 to 1,000 kilogram weight class to do direct freight. There's tens of thousands of routes that open up from that perspective. And then once you can do those higher, faster and heavier platforms, you can start using them as relays. And we see that this remote power market where there's industrials like mining, construction, and defense, with a lot of infrastructure that needs power provision, and typically they do that via essentially just shipping diesel and then running generators, but we can substitute that for remote power provision through these stratospheric drone relays. And that also unlocks the billion plus people who don't have access to grids, and we can begin to provide power connection to these people to bring them energy security. Like those types of applications are certainly near term viable, and then from there scaling into space, doing global scale transmission. That's the high level roadmap that we have.
No, it does sound like science fiction, and but as you've just said, it's viable and feasible. So what gives you the confidence that it can be done? Are you currently, obviously you're powering, drones, but what gives you the confidence that you can take this to a much broader scale?
Yeah, it's fascinating because I originally had the perspective that it probably couldn't be done. And going into this, I'm like, okay, well, what are all the reasons that it can't be done? And over time, we've just invalidated all those reasons. There's an operational pathway there, like the tech works. All of the pieces are coming into place to make it scalable. And seeing that all come together and seeing the magic of the technology working in our labs in the early phases and on the field with like early sort of runs and flight tests with drones, it's really just like it feels quite visceral. It sort of makes me feel that hang on, this actually can be done. So yeah, I mean, I feel like I've been quite a skeptic throughout the entire journey, but gradually I'm proving myself very wrong and sort of understanding how we can create our vision. And like I guess to take a step back and think more meta about this, the reason why like I'm doing this, even though I came at it from the perspective of like, what are all the risks? Why won't it work? Let's try and retire those risks. Well, the reason why I'm doing it still is because the opportunity to make the world a more abundant place and sort of provide energy interconnection is just so compelling that it's almost like I can't not be doing it, right? So yeah, I mean, it's just like really being quite magical, seeing it all come together. And I think the more and more I work on this problem, the more and more I realize that it's all possible. It's just a question of time and investment and development and sort of scaling, and that's exactly what we're doing right now.
Wow. So Billy, I guess a bit of context as well, just on your background and that of your team.
Mm.
What do you study, for example, or where do you get the grounding to think about these big ideas but develop them?
Yeah, it's also quite fascinating. So from my perspective, I have a formal education in math, and I worked as an engineer doing optimization on a bunch of sort of platforms. One was actually travel planning, one was industrial scale, I guess, battery energy trading. One was like fiber optic network optimization, and I built a few of my own sort of entrepreneurial platforms in like payments and battery virtual power plants, like that sort of stuff. So I had like a bit of a broad understanding of the energy sector and about networks and optimization and so forth. But I didn't have like a formal background in like laser power delivery or whatever. I don't think anyone really has that. It's a very nascent sort of sector and capability. So similar to like all of the people on our team, I mean, we have like 4 PhDs across optics, photonics, photovoltaics, and sort of photovoltaic engineering. There's a lot of different disciplines there, and like from an engineering standpoint, we have people in firmware, mechatronics, mechanical, in electronics, like every different type of engineering you could imagine, like goes into building this product. So yeah, it's really quite multidisciplinary, and I don't think there's anyone really who has that full stack, understanding of how such a system would work. But you can bring a lot of different people together, and you can bring a lot of disciplines together to make it work, which is what we've been doing. In terms of like how I sort of came upon the idea, it was actually, I mean, somewhat related to my engineering understanding of the energy sector, but also related to my lifelong kind of fascination for space and sci-fi and the idea of I guess exploring the universe. And that kind of led me to the Breakthrough Starshot project in 2016. I was reading this blog, Centauri Dreams, which is about interstellar travel and exploration and so forth. And it was interesting because it was talking about how you could build this 100 gigawatt class laser array and beam that amount of power into space, like tens of thousands of kilometers, to shoot a light sail off to Alpha Centauri, in human like lifespan level of time. And the interesting thing to me was, obviously I was fascinated by the idea of like sending a probe to another star, but also the idea of like you can build 100 gigawatt class laser infrastructure, and sort of scale it basically infinitely, and beam power over like tens of thousands of kilometers. And by the time it got to 2021 and all the technical papers came out for that, I realized that's exactly the capability you need to solve the current bottleneck in renewables and energy sort of infrastructure. And like furthermore, as Starshot was showing, the technology was getting exponentially better, faster, cheaper. So you just project that forward a couple of decades, and like everything becomes possible. So it was really just interesting to me, and like as soon as I had that insight, I was fully kind of sold and decided that I wanted to do everything I could to see if this thing could work. And as I said, so far it does seem to be working, which is really exciting.
Oh, that's wonderful, mate. Look, because there's been obviously a few, I guess, laser programs that are designed to for destruction, but nothing for for the good that you're proposing it for. So, let's dig into the tech a little bit. How does optical power transmission work at scale, and what's the breakthrough here?
Yeah, and perhaps an analogy which is at least informative is a similar trend was happened in nuclear, where first you deploy a nuclear bomb, and then you sort of decide and then you understand that you can actually use it for energy generation and bring a lot of abundance to the world. So a lot of these technologies that we do see have similar patterns of like we can deploy them destructively, but if you're innovative and sort of creative in the way you think, you can also understand how to deploy them for constructive and sort of generative applications. And that's a trend we've seen a lot, and it's exactly the same in lasers. In terms of how it works, it's quite simple really. It's you've got a laser on one side. It beams a single frequency or color of light. Although this color is outside of the visible range, it's infrared, so you can't see it. But it beams a single color of light to a photovoltaic receiver, which is essentially a special type of solar panel, which is tuned to that frequency. That solar or specialized solar receiver converts that light into electricity and charges the drone or supplies electricity to the whatever it's supplying electricity to. That's the basic concept. Operating it is more complex because you need to add on targeting, safety, and a lot of precision in both of those aspects. And you need to ensure that the way you deploy it enables, I guess, provision of energy without causing any safety and radiation exposure risks. There's new standards that enable you to do this. It's essentially just surrounding the sort of main power beam in a virtual protective housing, essentially a laser curtain, a low power sensing beam that goes around the main power beam and can shut off or reroute if there's any issues that could cause dangerous levels of radiation. But you put all that together, you have the lasers, the receivers, you have the operating systems, and you can turn this capability into a power transmission capability.
Wow. And so, mate, a lot of that infrastructure, currently exists, obviously, as you just mentioned. Is there other infrastructure that still hasn't even been thought of, here, and anything that needs to be launched into orbit to make this, I guess, viable on a mass scale?
Yeah, it's so with the relay systems to redirect power around, they're essentially just highly reflective mirrors. Because you're dealing with a single frequency of light or at two frequencies, technically, because you've got the safety frequency as well. But you can design the mirrors to be extremely reflective at those frequencies. And so the beam goes up into space in the sort of in our vision, and we redirect around extremely efficiently with space-based mirrors. Those materials all already exist. We think that there's basically nothing that we need that doesn't exist. The more of the question is like, how do you actually scale the infrastructure in a way that ensures it's economical? And from a design philosophy perspective, it's important to have modularity baked in. So those modular pieces are still like very challenging engineering problems, but they are just engineering problems, and it's just like a question of doing the engineering to scale.
Right, right. And you mentioned earlier, safety is obviously a key element of this particular program. How do you ensure safety, but then also, efficiency and energy loss? How do you manage the energy loss over distances, especially when we're talking about lasers?
Yeah, it's definitely a set of really interesting problems to solve. So when we came into this essentially with the belief that the technology was there and the key challenge was in operations. The question is, how do you operate these optical power networks at scale? Safety is a big part of that. The safety system works by essentially sending out a low power piloting beam, which is inherently safe, and that senses around the transmission pathway. We return that signal back to the transmitter, and once it's all clear, we have like a sequence of green lights that goes ahead and sets the all clear for the power beam to start transmitting through that pathway. And if any of those green lights at any point detect something awry, then the beam shuts off or reroutes fast enough that the radiation exposure that anyone could sort of encounter is always safe. That's the core of it. And yeah, I mean the the important thing here is again that concept of accessible radiation. So we consider that the radiation in the power beam is highly dangerous. It can cause burns, it can cause eye damage. Like you wouldn't want to be in the transmission pathway, but that pathway itself is a controlled space. So you can think of it similarly to like a laser disc burner, for example. So laser disc burner has a dangerous laser inside of it, but it's physically enclosed. And if you break that physical enclosure, then you can't actually access that high power internal laser because it shuts off through its interlock, it's called. And we have a similar concept applied to what's called virtual protective housing, and new standards enable you to also declass these systems for free space use if you have effective virtual protective housing. That's the core of how it works. In terms of efficiency, there's a couple things here. So the main sources of loss are on the transmission and reception. So right now, the cells work at between 50 to 60% efficiency. The lasers work at around 40 to 50%, but you've also got cooling, so you need to manage that. So net, you're looking at maybe 20% or so efficiency once you deploy the system with current technology. And that efficiency is always going to keep improving. The technology is improving exponentially. In aggregate, we think that we can move towards 50% efficiency over time, which is certainly enough from an economic standpoint to make renewable power transmission economical relative to, say, remote diesel or gas peakers. Now, in terms of managing that efficiency at sea level, you lose about 50% of the power over 20 kilometers. In the stratosphere, you lose around 50% over 2,000 kilometers. In space, it's effectively unbounded because there's no real sources of loss in space. So the way you deal with efficient transmission over distance is you just do it at a higher and higher altitude, which is exactly what we're sort of planning in that roadmap.
Right. Wow, that's very interesting. So, mate, let's look at the bigger picture. If you succeed here, who wins? Is it about enabling renewable energy, energy security, like you said, assisting those billion peoples in developing countries?
Yeah, I mean it's interesting, and the honest answer is we don't fully know. What we think is going to happen. Obviously, like all of the above, like everyone's going to benefit in the applications that I've mentioned. But there's also an entirely new design space that opens up. It's like once you have abundant energy, like wherever you are in the world, what can you do with that? And similar to how like mobile networks preceded mobile phones, it's possible that something really big happens in the future that we just don't even, or we can't even predict right now, because essentially we're just providing a new infrastructure layer. Um, Generally speaking, my belief, and it's a well substantiated belief, is that energy access is at the core of quality of life. The more access you can give people to energy, the better life gets. And what we're doing fundamentally is extending and improving access to energy, and we think that's going to just benefit everyone through better, cheaper, and more abundant access to power.
Well, you see it now in places like Papua New Guinea versus Australia. What's keeping Papua New Guinea in the back blocks is lack of energy.
Yeah,
As they call their power network up, or power provider up there, PNG Powerless. But you see, they've got a few other challenges, obviously, but energy is the one thing that keeps economies from growing. And you know, if you can develop this to the scale that you say it can be developed, that's a game changer globally.
absolutely, absolutely.
And so, mate, how do you see Aquila's work aligning with global energy challenges, so from storage to transmission bottlenecks?
Yeah, it's so with renewables, the thing that really entices me from an ideological standpoint is that there is 10,000 times more renewable energy in the world than we need as a civilization right now. And if we can just figure out a way to get that energy in the right quantities to the right places at the right times, then we can have a fully renewable energy system, essentially. And Aquila Lightway, what we're developing is in theory the infrastructure layer that unlocks that renewable future that we envision. So it's really about unlocking a lot of stranded renewable energy resource that wouldn't be accessible otherwise, and enabling the provision of that energy into global markets. Um, we don't necessarily see ourselves as competitive with I guess other areas of energy like generation and storage and transmission. What we see ourselves as doing is just extending and improving what's possible in the energy space, and extending access to power. So we think there's a lot of space for our sort of infrastructure layer to fit into the current energy environment, and that's sort of how we think about it, and what we're focusing on.
Right, right. And so, mate, what are the biggest blockers in your mind? Is it regulation, physics, funding, politics?
Yeah, it's well, with the upcoming field trials and pilots, we're certainly going to understand how much of a challenge regulations actually are. As of right now, we believe we have a certification pathway, and we want to validate that pathway in our market operations, and we'll see how that goes. Aside from that, yeah, there's a lot of uh, I guess ways in which the company could die and could be sort of destroyed. And a lot of those risks, I mean, it's just inherent to building something that's so, I guess, transformative and so different to anything that currently exists. So there's technical risks, like can we scale? There's operational risks, like will we be able to operate in the market at scale? There's obviously funding risk. We will need a lot of funding for a long period of time to unlock our vision, and that's just sort of part of the game at this point. So can we keep accessing and sort of using the amount of funds that are needed to unlock this vision over time, and so forth. So yeah, there's a lot of things that we'll need to work through, but the mission itself is so compelling that I don't doubt we'll have enough smart people and enough kind of backing behind us to complete that mission.
And I agree with you, and whether it be politicians or capital providers, I can definitely see there'd be a lot of patient capital out there willing to support what you're doing, because it has the ability to change the world. This is like this is like the new internet. It is like the new mobile phone. So I'm pretty sure there's a lot of people out there around the world who are willing to get behind you. But Billy,
Absolutely.
tell me, what's one milestone or signal in the next 12 to 24 months that would tell people that this is real? And obviously giving the politicians and the funders that belief to get behind you.
Yeah, yeah, absolutely. I think that it's just been in operations. So if we have a single pilot program running in the next 24 months with a drone flying, continuously charged by optical power in a security application, so it could be border security or base security or even like maritime security or sort of over the horizon monitoring applications. If we just have a single unit in operations with a drone flying effectively forever, I think that's going to feel real in a way that really unlocks that next level of scale.
Wow. Wow. And I guess, Billy, I guess finally, what do you wish more people understood about energy?
Yeah, I just think it's that point about abundance. It's like there's so much energy in the world and ultimately so much energy in the universe. We do not need to live in a world of energy poverty. We do not need to, I guess, reduce the amount of energy we're using. In fact, I'd argue that the way we create a better world is to accelerate the amount of energy we're using. And there's so much energy in the world, we can do that. All we need to do is deploy the infrastructure and deploy the resources to actually access the all the energy that's out there. So I just hope that people want to build a more abundant future, not a less abundant future, and that people are willing to solve the problems required and deploy the resources required to unlock that abundant future.
Oh, wow. Well, Billy, look, your vision, your insights, your enthusiasm, it's definitely something that I'm sure will make Aquila, become the next big thing in this world. And really wish you all the best. And hopefully we can catch up again for some updates along the way.
For sure, for sure. Thanks so much for taking the time. I really appreciate the conversation.
That was Billy Jeremijenko from Aquila Earth, proving that the future of energy might not be cables and wires, but light and precision. If you got value out of today's episode, hit subscribe and share it with someone in your network who thinks ahead. We want your feedback. What topics do you want us to cover? And who do you want to hear from next? Leave us a review or message us directly at Vaxa Bureau. Until next time, stay sharp, stay aware, and stay one step ahead.